Okay, so in the last class we have seen that in the graph theory approach, you have a few very well defined steps. One, the first step is to identify the standard tree. In any graph, you can draw the trees in very different ways, very many different ways, and out of that one would satisfy the requirements of being a standard tree. So, in it, what are the steps? First, it should include all voltage sources, then max capacitances plus maximum number of resistances plus the necessary number of so that is the logic by which we go in order to identify the standard tree. Once we have identified the standard tree, then there will be a co-tree, and immediately we can identify the state variables as the voltages across the tree capacitances and the currents through the co-tree inductances. So, that is it. So, the state variables inductances. So, we have identified the state variables. Then we have to take each state variable and obtain its differential equation. So, if you are starting with say a tree capacitance, so for tree capacitances now for the tree capacitances will be in what? They will be placed in certain branches that form the tree, and you have to for the capacitances you have to remember that when we said we started with the circuit, where our the tree structure was, we started from here, we took this one, we took this one, we took this one, and any other thing will complete it. So, this was the tree structure and that was the co-tree structure. And then when we started with this particular branch and tried to identify the equation for the tree capacitance VC1, then what was the logic then at that time? Where do we start? KCL at what? No? Yes, which cassette? The basic cassette. The basic cut set involving this particular branch. Okay. What is the basic cut set? It is a cut set, it is a cut set that includes only one tree branch. Okay. It is a cut set that includes only one tree branch. So, in this case how would you cut it? Yeah, you can cut it like this, you can cut it like that. So, there are various ways. Fine. So, you have no, this is the only way to cut it. So, for tree capacitances, write the Kirchhoff's current law for the basic cut set involving that branch, and for co-tree inductances so when we start with the co-tree inductance here, this one, how do we start? We start with the basic loop involving this particular branch. What is the basic loop? The loop that contains this particular branch, but only one co-tree branch. In this case, how do you write that? How do you identify that? This, only one co-tree branch, a loop. Okay. For co-tree inductances, write KVL. Can you see? Yes. And that more or less completes the story. If you start from these two premises, then you simply express the right hand sides in terms of the state variables, that is all, and that we have seen how to do. So, these are the 4 basic steps in obtaining the differential equations. When we write the KCL, the Kirchhoff's current law involves the currents, and the current through a capacitor is C dV dt, that immediately identifies the differential part. In this case, KVL will be the summation of the voltages. Out of that, one voltage will be the voltage across that inductor, where you will substitute it by L di dt, that immediately writes the equation. Clear? So, that is the procedure, and we have seen application of this procedure in some very simple circuits. But today let us try out on some relatively problematic cases. Say, suppose there is a circuit like this. This structure I am retaining because that is a very good structure to illustrate things, but I am only changing the elements. Suppose there is a voltage source here, there was an inductance here, no problem, let it remain. There was a capacitor here, let it remain. Let us replace this resistor by a capacitor, and here there was a resistor, let it remain, and there was another capacitor here, let it remain. So, all that we have done is that we have changed this resistor by a capacitor from the problem that we solved in the last class. Now, in this, obviously the graph will remain the same. So, let us in order to draw the graph, let us first write the basic graph in thin lines. And then we will join by thick lines as we identify the standard tree. Let us go ahead to identify the standard tree. Now, when we start, then the starting point should be the branch that contains the voltage source. So, this is done, included. It should include then maximum number of capacitors. So, this this. But now the moment we try to include another branch, say this one, it completes the loop. So, it no longer remains a tree. So, we find that we are unable to include all the capacitances. So, this one remains out. So, then this one becomes part of the core tree. These are the core tree branches. Fine. Good. So far no problem, let us go ahead with it. This was 0, 1, 2, 3, and you have the branches identified as A, B, C, D, E and F. We also have to give the directions of the currents, the assumed directions of positivity and negativity. Let us give it like this. And as I told you in the last class, these are arbitrarily assigned directions, and whenever the current actually flow in the opposite direction, it will have a negative sign. So, once we have identified this structure, how do we start? We start we start writing it by saying that my starting point will be, say, I am writing the equation for V, this is my C1, this is my C2, this is my C3, this is L, R, E. I am writing, say, for C1. Then C1 is here. I have to identify the KCL equation with the basic cut set. Okay. So, we have to identify the basic cut set that includes this basic cut set. Where is it? Here. Okay. So, this is the basic cut set. Right. The moment you have done that, we will write the equation as IB in going into IC minus IC minus IE is equal to 0. Fine. Notice the directions accordingly we have put it. Now, IB is what? IB is IL. Okay. IC was that C dV dt, C1 dV C1 dt. IE, this one, well, we have a problem here. Nevertheless, we can write it as minus C3 dV C3 dt. Okay. Or Vc3 is not a state variable. So, we need to do something about it, because as we have defined it, this particular branch, even though it is a capacitive branch, it was excluded from the standard tree. So, it is not a state variable. So, we need to do something about this. Okay. So, this is E. Instead of Vc3, let us write Ve, because otherwise we will maybe led to believe that this is a state variable. So, Ve. Now, where do we get Ve from? Ve will be obtained, V is obtained from loops. So, Ve will be obtained from the basic loop containing this branch. Where is the basic loop containing this particular branch? 0, 2, 3, 1, 0. Good. So, we need to obtain Ve. So, let us start from here. Ve minus Vf because it is in the opposite direction, plus V A minus V C is equal to 0, right. So, this is the loop 2 3 1 0 2. We have written this. V E I will put in the left hand side, V E, and we will shift other things in the right hand side. So, is equal to V F. What is V F? Okay. V C 2, V A E, and V C is no, V C is okay, done. So, we now substitute it here. What do we have? We are trying to write down the equation for this. So, let us put that in the left hand side and the other things in the right hand side. So, this now becomes d V C 1 dt. Let us keep the C 1 for now here. So, is equal to I L remains minus C 3. Now, all these will be d dt of this whole thing. Fine. We are substituting this term here from here. Well, expanded I L minus C 3 d V C 2 dt plus C 3 d E dt minus, is it going out? Let us take it like this here, C 3 d V C 1 dt. V C 1 is appearing in the left hand side as well in the right hand side. So, we shift it here. So, we get C 1 plus C 3 d V C 1 dt is equal to I L minus C 3 d V C 2 dt plus C 3 d E dt. Okay. Keep it, because as at present we can do nothing about it. We wanted to obtain this, but apparently this also includes this term and this term. We are very unhappy about it, but let us proceed. So, now we write the equation for V C 2. Where is V C 2? Here. And where is the branch that takes it? It is here. So, in order to write the equation for this, we will have to obtain a cut set that includes only this branch. So, it is yes. So, it is this cut set. Now, we will think in terms of cut set, not just the nodes. So, it is this cut set. The moment you write it, we can write the equation as it is V F going in, V F plus V E minus V D equal to 0. Oh, sorry, I, sorry, cut set will be Kirchhoff's current law, I F plus I E minus I D equal to 0, I F plus I E minus I D equal to 0. What is I F? The thing that I wanted, C 2 d V C 2 dt. I E is what? This term plus C 3 d V C V E dt we will not write it as VC3 because it is not a state variable VE, and ID is this one, it is VD by R. Okay, now we need to obtain VD. Where should it be obtainable from? VD. VD should be obtainable from the loop, basic loop, including this fellow, which is this. Okay. So we can easily write VD minus VA plus VF equal to 0. So we can simply substitute it here. Again we will keep this one this side. So C2 dVC2 dt plus C3, we know what VE is, we will substitute it here, d dt of this whole thing VC2 minus E plus VC1 minus 1 by R. VD is then VA minus VF fine. Now expand it, this appears twice, so C2 plus C3 dVC2 dt minus C3 dE dt plus C3 dVC1 dt minus this 1 by R VA E, right, E plus VF is VC2 okay. Again we see that we have arrived at an equation that includes both. So this was one equation and this was the other equation. This contains both this term and this term. This also contains this term as well as this term. So you can use these two to eliminate one to obtain the other. So it is two equations, two unknown problems you can easily solve to obtain this and that individually. Okay. So bring that is how we obtain the equations. Clear? Fine. I am not going to do this because you can always do that, it is not a big deal. Third equation, there will be three things. For IL, how do we write it? It will be the KVL including this basic loop. Where is it? It is yes, this one. So we will write VA, VB and VC only. So it will be VB plus VC, VB plus VC minus VA. Now VB is LDIL dt plus VC is something that you already know, that is VC1 minus VA is minus E into 0. So this is simple, DIL dt is 1 by L E minus 1 by L VC1. So this is the third equation. Notice one important aspect here. What did we do? Because we had this particular situation where okay, let us physically understand why did this problem happen, that one capacitor branch was excluded from the standard tree. It was because you can identify a loop that has only capacitances and the voltage sources, right. When that happens, the KVL over this loop tells you that all the capacitance voltages added together must be equal to this voltage which is externally applied, and therefore, all the capacitance voltages cannot be independent, at least one will be dependent. So, which one, let us not argue about it because any one could be. So, we in writing this particular standard tree, we have excluded this and therefore made this as the dependent variable. Notice again that this is not the unique choice of the standard tree, we could have done it other ways. For example, instead of putting this, we could have put in only this. In that case, this would be the independent variable and that will become dependent variable, clear. So, that is one thing. The other thing is that when we ultimately went on to solve it, we had a couple of equations from which we had to algebraically solve to extract this. This was not necessary in earlier cases. So, this is a peculiarity of this situation that results from this type of connection. Number 3, ultimately when you solve it, this term will remain. This term will remain in the equation, both E as well as this term. Now, this term says that a equation will have to be solved ultimately by some means, and that has the derivative of the externally applied force. This you might say that it is not a big deal. Yes, it is a big deal because this externally applied force could be anything. Could be sinusoid, in which case you are happy, if you differentiate it you get a cosinusoid, fine. But what if it is a square wave? You can easily apply a square wave because all that you need to do is to connect that kind of a circuit and turn on a signal generator with a square wave input. Then what? Then this particular thing will have to be solved, and when you write the program, obviously this will assume infinite values at the transition points. So, at the transition points this fellow will assume infinite values, your program will not be solvable, and in fact if you connect it like that, the circuit will have problems. Why? Because this term will actually be applied across the voltages. Okay. So, there will be enormous stress felt by the capacitances, clear. So, this tells you that even though on the face of it a circuit connected like this looks simple, there is no apparent reason why there is any difficulty with it, but there is a circuit theoretic difficulty with it. If you connect it really like that, then these elements will experience enormous stress. Large currents will flow through the capacitances, and that is why this gives us the education that we should never connect a circuit so that anywhere in the circuit you can identify a loop that contains only capacitances and voltage sources. Okay. If you do connect, or if some way this kind of circuit appears in some kind of a problem, then you have to do it this way. But if you have a choice as an engineer, you should never connect a circuit like that. Fine. Okay, let us do a problem in which a similar problem occurs with inductances. In this case, we have this circuit connected in a similar way. Here in place of the resistor, let us substitute it by an inductor, here also by an inductor, and here also here a resistor, and this one let us replace it by a current source, not a voltage source. So far we have not solved a problem with a current source, so let us do this. So this is the externally applied current I, and here you have the C, here you have L1, L2 and L3, here is your R. So 1, 2, 3, 0. Its graph is obviously the same. So let us identify the branches. Again, when we start the business, we have to start from by including all the voltage sources. There is no voltage source here, so we do not bother about it. Then we have to include all the or maximum number of capacitors. There is only one, so we start from here. Okay. Then we have to include the maximum number of resistors, which is here, so we include this first, and then the number of inductances necessary to complete the tree. So which one? Say we could do it this way, we could do it this way, we could do it this way, but not both, just one. So let us say we have done it this way. So the rest then becomes the co-tree. Let us put the numbers 0, 1, 2, 3 and the names A, B, C, D, E, F. The directions right. Now let us start the business. We start writing it by identifying the places where we want to write down the differential equations. So differential equations, the state variables will be what? The co-tree inductances. So IL1 here is in co-tree, this one is in co-tree. So IL3, all right, but this one is not in the co-tree, this one is not in the co-tree, and therefore the L2 will be excluded, and there is only one capacitor which is in the tree, so it will be VC only, there is no 1 2 because there is only one capacitor. So let us start by writing it for IL1. IL1 is here. So we need to identify what? The loop, basic loop involving this branch. Where is it? It is there. Okay. So let us write it. It is VB plus VD minus VF is equal to 0. Okay. VB is L1 d IL1 dt. VB is this. VD as yet we do not know. So let us take it this side, minus is equal to minus VD is L2 d I will write because this is not a state variable, dt, and this one is plus Vf is R I F. Okay. Now at this stage we need to identify what IF is okay, and we need to identify what ID is. ID should be obtainable from the cut set where only this one appears. Where is it? This whole thing here to cut, right? So we need to cut like this in order to get this cut set out. The moment we have done that, we can write cut set A, B, D, E. So we write I A plus I B minus I D minus I E is equal to 0. Okay. Going from the upper subgraph to the lower subgraph is positive. So this is plus, this is plus, this is minus, this is minus. Fine. I A is I. Okay. I B is IL1, which is a state variable. We are happy. Minus ID is something that we want to find out. IE is that is IL3 is equal to 0. So we have got it. We extract it and substitute it here. We also need to find out this one, IF. IF should be found from the basic cut set that includes this branch. Where is the basic cut set? This one. So that is obtainable as IF this way plus IB plus IA is equal to 0. Substitute these two. IB we know it is IL1 and IA we know it is this I. So we substitute it here. After the substitution we get L1 DIL1 dt is equal to minus L2 d dt of I plus IL1 minus IL2 IL3 plus R minus I plus IL1. Okay, I have substituted. Now expand it, you will get RIL1 minus RI, then the derivative terms, plus we can get one term this side. So it will become L1 plus L2 DIL1 dt. This term goes here. So the remaining terms are L2 di3 dt minus L2 di dt. This is the externally applied current. Again you see here we have the IL1 dt appearing here, the IL3 appearing here, and di dt also appearing in the same way that happened for the last circuits. Again if you write down the equation for IL3, that is a state variable.
Sir, in the first equation, R minus plus I minus IL1.
Let us see, IF plus IB plus IA is equal to 0. The last term you are talking about, right? So we wanted to find out IF. So both will be minus.
No, sir. One will plus. IA is minus I.
I
IA is minus I. So IF will be equal to I minus IL1.
okay.
So there will be plus I minus IL1.
These two will have opposite signs, all right.
Yes, sir.
Huh? But this one goes to this side and it is here.
Yes, sir.
So R times
Minus IB
minus IB
plus IA.
like IA is I.
Yes, sir.
Huh?
Plus IB.
Okay, okay.
Sir, if IA is plus I, then in that previous equation also will have IA as minus I. I will be
Here,
Minus.
yes, you are right. Because I have given the sign this way, and here it is this way, so it is just that. Fine, you are right. So for IL3, what do we have? Which IL3? We need to identify a loop that contains this one. Where is that loop? This loop. So we will write VE is equal to minus VC plus VD. Okay. Then we will write L3 D DI, sorry, DI L3 dt is equal to what is VC, okay, minus VC, this is a state variable, so we are happy, plus VD is this term, which, okay, we had the same problem here, we will extract it. So plus L2 d I L2 dt, but this term we need to substitute is exactly in the same way as we have done here. So substituting this equation, we have, oh, I should have written ID. When you substitute, you get is equal to minus VC plus L2 d dt of this whole thing, which is I, which is minus I, right, because this minus I plus IL1 minus IL3, okay. So now you get this thing out in the same side, you have L2 plus L3 of DIL3 dt is equal to minus VC plus L2 DIL1 dt minus L2 di dt. Fine. Again we have this equation and this equation. We have two equation, two unknown problem, solve it. And there will be another state variable which is Vc. For it, the equation will be trivial. For Vc, the equation will have to be obtained from the, from where? Containing this, and where is it? Here, this cut set. So, quickly write the equation. You will write I C is equal to I E minus I A, and then you will write the equation. I am not bothering about it. C d V C dt is equal to I L 3 I A, it will be plus I, right, it is ulta in the opposite direction. So, you can easily get the C in the other side, you get the equation. Well, so we have more or less understood that in this case also you run into the same problem. We have the equation involving a couple of equations from which these two terms need to be extracted. A algebraic problem can be solved, but what we end up with also will contain this, and this term will mean that the externally imposed current will have to be differentiated in the equations, which will be difficult to solve in reality in computer programs. And in fact, when you actually connect the circuit in this way, this will cause actually a problem, because this cannot instantaneously vary. If it does, then di dt will be applied as a voltage on these inductors. Now, why this problem happened? Can you identify why this problem happened? Yes, something forms that contains only with the current source and the inductors, this loop, current source and the inductors. Therefore, all the currents in the inductors cannot remain independent variables, and whenever that happens, there is a practical circuit problem, and you should understand that you should never connect a circuit like that. Okay. Further details of this kind of circuits will come back, because these are something that is very rarely understood by electrical engineers. So, we have to understand it even more carefully. We will come back. But now, let us give you a few problems to solve at home before we go into the next kind of topic. Solve these problems. The source current, source voltage L, R1, R2, C1, C2. Fine. Number 2, there is a source here, then it is connected to resistance, to another resistance here. Here you have a resistance, and then okay, let us replace it by a capacitance. Then you have another voltage source, an inductor, a resistor, and maybe let us connect a current source here. Another voltage source, resistance. Okay. So, there are many resistances R1, R2, R3, R4, and this is L. This is EA, EB, and EC. Fine. Have you copied? Fine. Third problem. third problem, you have got a voltage source connected with a capacitor, with an inductor, with another capacitor, with a resistor here, and we have resistor coupling here, C1, C2, L, R1, R2, E. Okay. Oh, have you copied? Fine. One important exercise is where you identify the problem where, okay, let us first draw the circuit. Capacitor, supposing there is a resistor here, an inductor here, a resistor here, and there is a capacitor here. Okay, will the mesh current method be applicable to this? Agreed? No, it will be applicable because it is not actually a overlap. You can easily break it by moving it from there to. Okay. So, whenever you are given a circuit, first think, just because it shows with a overlap, that does not mean it is a non-planar circuit. It can be made a planar circuit. Sometimes you also think in this line, but let us handle some truly non-planar circuit. I will give you. First, let us take another planar circuit. We have, because most circuits are actually planar, in VLSI to these days we are starting to use non-planar circuits. So, you need to understand that also. Fine. Copy it. Done? It's not visible. So, this is the circuit. Now, I will give you just one more problem to solve, which is a non-planar circuit. So, this is a hopelessly non-planar circuit. So, by doing nothing you can get it into a plane. So, write down the graph of it and solve this problem. Okay, fine. That is all about it today.